and welcome to this lecture in the hands-on large language models series. Today we are going to learn about the topic of quantization. So we'll understand what is meant by quantization and why it is so important to understand when we are learning about large language models. Let me switch to a different color over here so that it becomes easy for all of you to see. Okay, so in the previous lecture we saw that there are several ways in which we can enhance the LLM output without needing to fine tune the model itself, and these ways can be classified into buckets such as model input and output, adding memory to the model, dealing with agents, and all of these things come under the unified framework of chains. We also looked in detail about the Lang chain framework. We understood that Lang chain allows us to build very powerful large language model applications predominantly because it can allow us to chain different models together. We can chain different prompts, we can chain memory modules, we can chain retrieval modules, and we can even chain agents together. When you modularize large language models this way, and when you chain different things together, it leads to really powerful LLM applications. Alright, so in today's lecture, we are going to learn about the first component of these four, and that is model input and model output. So what is meant by model IO? The main thing which we are going to learn today is how to load quantized models and what is meant by model quantization and why it is really important. So let me write it down over here. Model quantization. Model quantization, what it means and why do we need it. Alright, so let's get started with today's lecture. Before we start making use of Lang chain features, which are a huge number of features which they have, first we need to load the model itself, right? First we need to load the large language model, and then we will ask several questions to the large language model. We'll be asking prompts to the large language model, we'll be defining agents, etc. But the first thing is to load the model itself. Now here is where the problem comes in, because large language models are huge. Some models have billions of parameters, right? For example, if you look at GPT-3 model size, it has 175 billion parameters. That takes up a lot of memory. It slows up the compute and it leads to a huge amount of computational time and expense. So it is very important that we are loading the models in a very efficient manner. You must have heard of something called as GGUF models, right? If not, it's totally fine, but let me show you what I mean. If you search about Microsoft Phi 3 model, you will get this Microsoft Phi 3 Mini 4K Instruct, right? It's a 3.8 billion parameter model. But apart from this model, you will find documentation for one more model which looks exactly the same, but there is the added 4 letters here, and those 4 letters are G, G, U and F. So you might be thinking, what exactly are these 4 letters? What do they mean? And what does it change for the large language model itself? So the real reason why these 4 letters here exist is because this is a quantized model, and that is what we are going to understand today. So the number of parameters, if you see here, it's the same. It's 3.8 billion parameters. And here you see the number of parameters is the same, 3.8 billion parameters. The only difference is that here the parameters are stored in the GGUF format, which we are going to learn about shortly. So the main goal of quantization is that we are going to load a compressed version of the original model through a method which is called as quantization. What this does is that it loads the same model with the same number of parameters, but this is a technique which will reduce the memory footprint. So quantization is a technique which reduces the memory footprint of the model, which means that it takes up less space and we can even do the compute more quickly. So there is this terminology called as VRAM, and let me show this to you what it means. VRAM. So VRAM is a type of computer memory that stores and manages graphics data for a computer display. Now if your computer or laptop has high VRAM, you can run more powerful large language models. If your computer or laptop has low VRAM, then it becomes difficult to run powerful large language models, right? So what quantization does is that it takes up less amount of your VRAM space. So even if your VRAM is low, you can still run a quantized model, but it might be difficult to run a larger model which is non-quantized. Alright, so before we understand what actually is quantization, we need to first understand how numerical values are represented, and once we understand that, we will understand how the weights of a large language model are represented through quantization. So let us try to see how numerical values are represented. One of the most common ways to represent numerical values is in terms of floating 16-bit values or floating 32-bit values. So if you want to, let's say, encode a numerical value which is pi, for example, and if you want to encode this value as 16-bit, so there are certain conventions to do this. So here you can see 1, 2, 3, 4, 5, 6, 7, 8, there are 16 bits over here. Usually the representation is divided into 3 parts. The first part is the sign, the second part is called as the exponent, and the third part is called as the significant or the mantissa. Now if you see, this is one representation of pi. So the first is the sign, right? Then the second is the exponent, which is 1, 0, 0, 0, 0, and then we have some significant over here, which are zeros or ones. Now the way we calculate the actual value from these is that we do something like -1 raised to sign. So if this is 0, then -1 raised to 0 will be 1, which essentially indicates it's a positive number. If it's negative, then this will be 1, so it will be -1 raised to 1, so this will be -1. Then you multiply by 2 raised to something, and that something is usually exponent minus the bias. So the exponent is so there is 1, 0, 0, 0, so it's 2 raised to 4, which is 16, and the bias is 2 raised to b, which is we have 5 bits over here, right? So the bias is 2 raised to 5 minus 1, which is 15. So exponent minus bias is 16 minus 15, which is equal to 1. So then -1 raised to sign multiplied by 2 raised to exponent minus bias, which is 2 raised to 1, and multiplied by whatever this represents, right? So now we have 1 here. So this is 1 into 2 raised to -1, plus we have 0 over here, plus 0 into 2 raised to -2, plus we have another 0 over here, plus 0 into 2 raised to -3. We have 1 over here, so it will be plus 1 into 2 raised to -4, then it will be 0, 0, plus 2 raised to -7, and plus rest all are 0. So if you add all of this together, you will get 0.570325. So now, so this will be 2 raised to 0, which is by default 1 is added over here. So 1 plus all of this addition, which is 0.570325. So if you do this multiplication, which is -1 raised to the sign multiplied by 2 raised to exponent minus bias, which is 2 raised to 1, multiplied by 1 plus whatever this value is, so that's 0.57, you will get a value which reads 3. Let me write this down over here. Yes, you will get a value which essentially reads 3.140625. Now if you look at this value, it is closer to 3.14, and you should look at the number of digits which are there after the decimal point. So if you look at the number of digits which are present after the decimal point, we have 3.140625, right? So 140625, there are 6 digits which are present after the decimal point. Now what I am going to do is that I am going to show a 32-bit representation, and then we are going to compare the 16-bit representation with the 32-bit representation. Alright. So I showed you the 16 bits right now. Now let's see 32-bit representation. So what changes in 32 bits is that we have 1, 2 up to 32 bits, and each has values 0 or 1, right? So it's binary. And the way we calculate is the same, minus 1 raised to sign, which is 0, multiplied by 2 raised to exponent minus bias, that also is going to be 1. But what changes is this last part. Now we have so many more digits here, right? We have actually 16 more digits here than we had in the 16-bit representation. So if you find the value of the last part, it's 1.5707964. So if you do this calculation, this number turns out to be 3.1415927, etc. Whereas if you see this number, there are only 6 digits after the decimal point. Whereas here you see there are 6 plus 6, 12 plus 4, which are 16 digits after the decimal point. So what I have done is, now the original value was this 3.1415927. If you represent this number as the 32-bit value, it can be represented as something like this. If you want to represent this number as a 16-bit value, it can be represented as something like this. Now I want you to compare these two values. What is the difference which you see? The main difference which you see between these two values is that at first glance they look kind of similar. Both are 3.14, 3.14, but the 32-bit representation has a much higher precision. What is precision? The number of digits after the decimal point. It has a lot higher precision than the 16-point representation. The 16-point representation has a much lower precision. That's the first takeaway from today's lecture. More bits equal to more precision. So if you have a number, right, if you have a floating point number, any number, let's say this is the weight, one particular weight out of 175 billion in the large language model, and if you represent this number as a floating point 32, whereas if you represent this number as a floating point 16, what you will, the first conclusion which I want to tell all of you is that, and let me share that with a different color, the 32-bit representation has more precision, whereas the 16-bit representation has less precision. That is the first learning. Let's say this is one weight of the LLM. Now let's look at the second learning, right? So it turns out that the more bits we use to represent or encode a number, the more memory it takes. Remember I told you about VRAM, right? So the more number of bits you use to represent a floating point number or a weight, it takes more memory. And the memory which is taken is roughly given by this formula, is number of bits divided by 8 multiplied by number of parameters. Now let's say we have a large language model which has 70 billion parameters, right? And in first case we use a 64-bit representation. So that will take on an average 64 divided by 8 into 70 billion, which is 560 gigabytes of space. If you use 32 bits, that will take 32 divided by 8 into 70 billion, which is 280 gigabytes of space. Whereas if you take 16 bits, you will roughly take 16 divided by 8 multiplied by 70 billion, which is 140 gigabytes. Now, most large language models are by default represented with 32-bit, which is also called as full precision. So if you see this Microsoft version, Mini 4K Instruct, we can assume that each weight is represented by a 32-bit representation. Whereas if you look at this 4K Instruct GGUF, I think this is a 16-bit representation, or yeah, this 4K Instruct, this is a floating point FP16, which means that it's a 16-bit representation. Let's look at this right now. So this Phi 3 Mini 4K Instruct GGUF, here is this FP16, see, FP16.gguf. What this FP16.gguf means is that it's a floating point 16, which means that here we saw 16-bit representation, right? We saw 16-bit representation over here. So this GGUF, fp16.gguf means that every weight of the large language model is represented as a 16-bit representation or 16-bit encoding. So that takes much lesser memory than if you use the by default 32-bit. And roughly how much less memory it takes? Roughly half of the memory is saved if we use a 16-bit versus 32-bit. So now you must be thinking, okay, wow, then why don't we always use these quantized versions? Well, there is a trade-off, right? And that trade-off is with respect to precision. If you use 16 bits or if you use 8 bits or even go lower, the memory consumption will go on decreasing, but at the same time, your precision will also go on decreasing. So if you draw a graph right now, so here I have, let's say, 8-bit, here I have, let's say, 16-bit, and here I have, let's say, 32-bit, right? First, if I plot the memory consumption is like this, which means it's the lowest, and the memory consumption increases. So this is the memory consumption. Now the second thing which I'm going to plot is the precision. So the precision also increases, see. So if you are using an 8 billion model, the advantage which you have is that you have low memory consumed on your device, but you also have low precision. So that's the trade-off which you are making here. But generally, if you see here, this also looks almost like our original value, right? So that's why quantized models actually work, because even if some of the precision is lost, it's still enough for us to predict the next token accurately. It's enough for the large language model to do tasks which it is trained on, even if we lose some amount of precision. In most practical situations, we don't need to have an extremely high amount of precision for large language models, and that is why quantization works. So now once you understood these two lessons, more bits equal to more precision, and more bits is also equal to more memory consumption. After these lessons, this is where quantization actually comes into the picture, right? So quantization, the whole goal of quantization, or I should say rather the methodology behind quantization, is that we reduce the number of bits which are needed to store every weight of the large language model while attempting to retain most of the information. That is the delicate balancing act which we are playing. We are reducing the number of bits to represent every weight, but at the same time we are attempting to retain most of the information. So we don't want our model to not predict the tasks in a better manner just because we lost a lot of precision. We want the output to be equally good, but we want the memory consumption also to be very less. So what we want is that a quantized model leads to a loss in precision, and that's fine, but it leads to a much faster model. It uses less VRAM, and it's almost as accurate as the original model. If these conditions are satisfied, then it's always a better idea to go ahead with quantized models, right? Okay, now I hope you have understood theoretically what is quantization. As in all of the lectures which we conduct, I also like to give some practical intuition so that you will never forget quantization. There are two things which I want to illustrate. The first is through image, right? Let's look at the image on the left. It has a huge number of colors, and it's a very high resolution image. Now, I want you to look at the image on the right. What if I tell you that the image on the right is an image only made with 8 colors? 1, 2, 3, 4, 5, 6, 7, 8. So in an essence, it's like quantization. Why? Because we are trying to encode the same amount of information but with lower bits. So here in the original image, there can be huge number of colors. There can be a mixture of colors, gradients of colors. But here I am just using 8 colors, and already you can see that the left and the right image look almost the same, right? To our eye they look the same, but if you zoom out onto this chocolate chip over here, this is the original, and you can see that it is a bit more detailed, whereas this is the quantized. Now see, if you look at the quantized, you can see that it's already quite pixelated. See over here, it's only when you zoom in that the differences are clear. Similarly, here it's only when you zoom in, which means that it's only when you analyze these later numbers, you see that here those numbers are not there. So here also what we are trying to do is that we are trying to the same thing. We are trying to use less amount of memory for representing this image, but we are trying to be as accurate or as correct as the original model. So here also the right image, we are trying to make it look as correct as the original left image, but we are trying to do it using as less amount of memory or bits as possible. Never forget, even if you forget quantization, that's fine, but always remember these cookies or these biscuits which I am showing you. Images always have a powerful meaning and they have a powerful impact. So although we might forget text, we might forget lectures, but it's very hard to forget good images which we see. So this is what I like to call as the cookie analogy for quantization. The second analogy is the analogy of time, right? If asked what time it is, you might say that the time is 2:16 p.m., which is 14:16, which is correct, but it's not a fully precise answer. You could have instead said that it's 14:16 and 12 seconds, which is more precise, it's more accurate. However, mentioning seconds is not helpful most of the times, and we can simply say just minutes, right? Even if you say 2 minutes and if you say it's 16 minutes past 2 o'clock, it's fine for me. I don't need the seconds. So quantization is a similar process that reduces the precision of a value, which is we are removing the seconds without removing the vital information, which means we retain the hours and the minutes. So another way to remember quantization is that we are retaining the hours and the minutes, but we are letting go of the seconds. Why do we unnecessarily need so much detailed amount of information? That's the main idea behind quantization. One more thing which I want to illustrate before we understand quantization in a bit more depth is that until now we looked at the floating point 32 and floating point 16, right? There has been a very interesting research regarding 1-bit LLMs also. So researchers have discovered a way that instead of floating point 32 or floating point 16, we can even achieve an incredible performance by scaling down the LLMs to 1.58 bits, which are also called as 1 bit. So this architecture is called bitnet B 1.58. So here if you see, the numbers are not even represented like these in this much precision. The numbers are just represented as -1, 0 and 1. Isn't that incredible? We are now letting go of everything. We are maybe just returning the hours. We are letting go of the minutes also along with the seconds. So if you represent the numbers, so in the first case you see we are representing the weights as floating points. In the second case we are representing the weight as just 0, 1 or -1, that's it. And what this author proved is that this second case, of course it leads to very low memory requirements, because instead of encoding every number as 16 bits, we are now just doing in 1.58 bits. But the real amazing result is that they got very nice performance out of this 1-bit model or this 1.58 bit model. So they have some images or they have some so look at the memory reduction. So if you use the Llama large language model, 700 million, whereas if you use bitnet B 1.58, I think the Llama LLM is like 16 bit or 32 bit. It takes 2.08 GB, whereas this only takes 0.8 GB. That's almost a 3 times reduction, 2.6 times reduction in the memory. But at the same time, they illustrated that the performance is equally good. So then why not use these smaller models if the performance is equally good or the same, right? In fact, if the models are this small, they can even be loaded on our phone or they can be deployed on CPUs. So that's why the authors conclude that low bit models or low bit large language models are more friendly to CPU devices, which are the main processors used in edge and mobile devices. Microsoft went one level ahead. So this research came out of Microsoft research. They went one step ahead and they open sourced this repository called bitnet, which we can use. It's the inference framework, which means we can download it and run it on our laptop to test how it is working. It has around 12,000 stars. It's still a bit slow on my laptop. So my laptop is 8 GB RAM. It's still a bit slow and it does not produce very coherent results, but I think within 2 to 3 months we will be at a stage where everyone in the world can download an LLM on their laptop without an internet and run it. The memory footprint can become so low using this 1-bit LLMs. Okay, so these 1.58-bit LLMs are also an example of quantization. Alright, so now what we have to do is that I want to just show a couple of more things so that you understand quantization in a bit more detail. So here you can see, let's say I have a number and this is the floating point 32-bit representation of the number, which I have shown over here. What quantization does is that we take this number down from, let's say, 32 or 16 to a 16-bit representation. So here you can see that once we take the number down to a lower representation, the minimum value decreases, the maximum value also decreases, which means that once we go from floating point 32 to floating point 16, the range of values which we can cover decreases. So you can see the range here, this range is much smaller than this range. This range is much higher. And what also decreases is the precision. So here there are values which lie very close together to each other, right? But here the values which will lie far apart from each other. So the range is reduced and also the precision with which we can encode values reduces. But mathematically you can think of mapping numbers like this. You first map the endpoints. You map the endpoint of floating point 32 with the endpoint of floating point 16. You map the endpoint of floating point 32 on the positive side with this. And then based on that scaling factor, every single point here can be mapped to a lower floating point representation, and that's how the quantization is done in practice. But one thing which I want you to take away from this figure is once you do the quantization, it leads to a lower range and it also leads to a lower precision. Now some of you who are inclined towards mathematics related to quantization, I will not go into too many details. I will point you all to an excellent resource, but I just want to provide an intuition of the mathematics used behind quantization so that you can dive deeper into it, right? So let's say if we want to quantize from floating point 32 to an integer 8. So since it's integer 8, the values it can take is from minus 127 to 127, right? So the first step to do this quantization is to first calculate the scaling factor. The scaling factor is basically what is that factor with which every number here will be multiplied with to go to the quantized value. And to get this factor is fairly simple. So what we do is that in the numerator we just have 2 raised to b minus 1 minus 1. So here b is 8. So the numerator will be, so b is the number of bytes that we want to quantize to. So here we want to quantize to 8 bytes, right? So b is equal to 8. So this will be 2 raised to 8 minus 1 minus 1, which will be equal to, so 2 raised to 7, which is 128 minus 1, so that is 127, and divided by alpha. So alpha is the highest absolute value. So here you can see this is alpha, which is the highest absolute value, and that is 10.8. So now we have a scaling factor which is 11.76. What this means is that we are going to take every number here and then we are going to multiply that number with 11.76, and that will give us a new number. So let's say I take a number here, this number will be multiplied by 11.76, I'll get this. I'll take this number, it will be multiplied by 11.76, I'll get this number. Similarly, the scaling factor can be used. So here we can see that this 11.76 can be multiplied by any number which you want to consider here, and then it will give me the new number in the int 8 scale. And then similar to the way we do quantization, we can also do dequantization, which means that instead of multiplying by s, we now divide by s. So if we want to go back, from here to here, we just divide by s, which is the scaling factor, and then we'll be taken back. So I'll just mark the going back with a different color. So I'm marking the dequantization with green color. So in dequantization, what you do is that you just take the values and you divide by s, whereas in quantization, which I showed you over here, the arrow is pointing in this direction. You just take the value and you will multiply by s. That's the difference between quantization and dequantization. So here I am just showing the process of first quantization from floating point 32 to integer 8. We'll take every value, we'll multiply it with the scaling factor, and then we will divide it with the scaling factor to dequantize it. So you will see quantization and dequantization is not lossless, which means that there is a loss here. How do I know there is a loss? So if you see 5.47, it's quantized as 64, but it's dequantized as 5.54. If you take minus 4.57, it's quantized as minus 54, but it's dequantized as minus 4.59. So just remember this in mind, or just keep this in mind, because here the number which we are multiplying scale factor, its precision is not very high. So that's why there is always some loss when we recover the original value. So what I want to mention is that dequantization is not lossless, which means that we always lose some information when we quantize. That is extremely important for all of you to remember. Although our memory requirements are now less, our LLM maybe speed, training inference speed might increase. We are always losing some information, but the main thing is we are willing to let go of this information as long as our performance is good. So I hope this is enough mathematics and intuition for all of you to develop an interest in this very interesting topic, which is also, by the way, a great topic for doing research. This field is relatively new, this field of quantization, and if you start learning about it, it can be an interesting and easy way to get into large language model research. There is an excellent blog post, which is the best blog post I have read on quantization. It's called A Visual Guide to Quantization. I'll share the link to this. Many of the images I'm showing in today's lecture are borrowed from this blog post. It's extremely detailed, and it also explains the mathematics in a lot of detail. It also says that there are two types of quantization really. There is something which is called as post-training quantization, and there is quantization aware training. I did not go into too many details of this, but maybe I'll have a separate lecture on this in this series. The last thing which I want to mention is that when you are using pre-trained or when you are loading large language models, you will often encounter this format called GGUF. In fact, here is a Google Colab interface which I have opened, and I am using Llama CPP. And let me show you what Llama CPP is. So it's an inference framework in C and C++ language. It has 70,000 stars, which means you can use this repository to query different large language models and to get their responses. Now, what I have done here is that I have mentioned the model path. Now see, the model which I have mentioned is the Phi3 Mini 4K Instruct floating point 16.gguf. See, this is exactly that model which I was showing to all of you over here. So I just want to explain a bit more about GGUF so that all of you again have an intuition for what exactly is happening in GGUF. So essentially the key thing to remember is that GGUF is a file format, right? We can use GGUF to offload any layer of our large language model to the CPU. That's the main advantage of GGUF file format. So when we are using GGUF models, it allows us to use both the CPU and GPU when we don't have enough VRAM. Now the way GGUF works is that you have layers in large language models. So the weights of a given layer are split into super blocks and sub blocks. And you remember we saw scaling factor over here for quantization. There is a separate scaling factor for the super block, and there is a separate scaling factor for the sub block. And that's how weights are quantized in the GGUF file format. Again, I'm not going into too many details here, but for readers or for viewers who are interested, in this blog post, the author has explained a lot of details about the GGUF file format, and let me take you to the place where that is explained. Yeah, so see here, this is where GGUF is explained. and it's a quantization method which is updated frequently and might depend on the level of bit quantization. But the author mentions this general principle of super blocks and sub blocks and how the GGUF quantization is actually done. But for all practical purposes, now you have to remember that GGUF is really helping a lot of researchers deal with large models. So GGUF LLM Reddit, if I just put, there is here you can see GGUF appreciation post, allowing me to host large llama models on my home computer. With only a slight performance loss, you can gain a load of efficiency. And here you can see there are so many people who are commenting that GGUF file format is a community effort. So here you can see, you can open this link over here and you will see this is the main repository under which the GGUF file format was developed. In fact, there was a request for GGUF file format specification defines a complete specification for the proposed GGUF file format, which should generally describe models to be loaded by any compatible executor. So yeah, there is a huge amount of theory behind GGUF itself, which I am not going into right now. But for now, just remember that GGUF models help you with quantization. So less VRAM is occupied on your laptop or on your computer, and similar or equal amount of performance might be obtained with a large language model. What I'll recommend to you right now after this lecture is that I'll share this Google Colab code with you. This is a pretty long code because we'll be having subsequent lectures on different aspects which I'm showing here, such as memory, retrieval and agents. But in the meanwhile, what you can do is that you can just run the first code cell using the instruct fp16.ggf, and then you can just remove the fp16 part and just use this 5.3 mini 4K instruct and just see the performances in the inference quality for different types of prompts which you give. So that way you yourself will see whether GGUF has lower performance, how much memory it takes, you can analyze it. So when you load this model, it will show you how much memory it's taking. So you'll yourself see that GGUF takes much lesser memory and it has an equal or comparable performance without using GGUF. So this brings us to the end of today's lecture, where we learned about quantization. We learned about two things basically. First, to represent numbers, we can represent them as bits. More bits equal to more precision, and more bits also equal to more memory consumption. So the whole goal of quantization is to represent model weights in as lower number of bits as possible, at the same time maintaining the results which you get from the model itself. So quantization reduces the number of bits while attempting to retain most of the information, right? There are two analogies which you can remember regarding quantization. So first is the cookie analogy, which I showed in this here, image over here. As we go from left to right, the number of colors which we use decrease. So that reduces the memory or the number of bits, but both these images almost look the same. Secondly, quantization is the process. It's like removing the seconds. If someone asks me what time is it, I can say it's 4 p.m. 3 minutes. I don't need to tell the seconds. So quantization is removing the seconds while at the same time preserving the information. So this is the clock analogy. So remember clock and cookie analogy of quantization. We also saw that quantization leads to lower range and lower precision. And finally we understood mathematics. So there is something called as the scale factor, which is always used when you learn about quantization mathematics. And we had a very brief introduction to the GGUF file format, how it can be useful to offload any layer of the large language model to the CPU. This essentially allows you to use both the CPU and GPU when you don't have enough VRAM. So that's the power of GGUF and quantization. So there are also models which are so here floating point 16, right? There are also models which are lower than floating point 16. For example, in this blog post you will see that there is also a description about int 8. So there are also models int 8. In fact, as I showed you in this paper, we can go farther below and just drop down to 1-bit LLM, where every weight is just -1, 0 and 1. So quantization is the pathway towards getting models so small that you can download them on your desktop, run LLM inference on your desktop, and once you download them, you don't even need internet. So quantization is the pathway to making LLM inference equitable to even the poorest regions of the world where internet connectivity, memory is not there. So you need lower memory, you don't have internet connection, no problem. You can use 1-bit LLMs, download them. It will not take too much memory, and once you download, you can use them for inference. I think this is the future of equitable large language models, and that's why quantization is such an important topic of research right now, which you can also dive into. Thank you so much, everyone. I hope you are liking these lectures. In the subsequent lectures, we'll look at chains, then we'll follow it with memory, and then we are going to look at agents. So thanks everyone, and I look forward to seeing you in the next lecture.